Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our exercises on the topic of functions of several variables. So yeah, let's just hop right into it. So here again, we're going to be practicing this idea of identifying the visual or the graph of a function of two variables. Yeah, so far we're doing functions of two variables. And then after that, we're gonna talk about contour maps. So yeah, this is just gonna be one long video if I'm slow at doing this, but yeah, we'll see. Okay, so let's just hop right into it. Okay, so number 7, I'm just pulling up the homework. Basically, we want to match the function with its graph. I'm not gonna do that. I'm basically gonna sketch the graph myself or try to find some, but basically kind of identify the graph of a function. So maybe I might just do that. Okay, so how do we do this? Well, letter A, let me, so I have my function f of xy, which is 1 over 1 plus x squared plus y squared, right? So here, how do I find a graph? Well, we have three things that we did. One of them was finding its domain. Another thing that we did was, well, identifying the type of graph. Is it an ellipsoid? Is it a paraboloid? Is it a hyperboloid? That type of stuff. And then lastly, what we did was find intercepts. Right? So those are the three things we did. I might just do all of them right here. Okay, so to find the domain of this thing, my only restriction is that my denominator should not be 0. That's it. So I'm saying that this thing should not be 0. And so, okay, let me put this a bit down. So I guess what I can say here is that, okay, this thing should not be equal to -1, right? What else can I say? Um, this is an equation of a circle. It's kind of impossible to, yeah, this is impossible to look at, right? There's no such thing as a negative radius. Yeah. So maybe, I don't know, maybe that won't work. Not super sure. Okay. Maybe if we try identifying its type, maybe that will work. So if I take out my, okay, so here we have this thing. We have z is 1 over 1 plus x squared plus y squared. This is my z. If I take out my z, what am I left with? Well, I can't really, yeah, I can't really determine what in the world this is. If I take out my z, I'm gonna have like what? Um, there's gonna be some k maybe. I'm not sure. There's gonna be a value, some constant value, and I'm gonna have to like multiply. I'm gonna multiply it with some k value, which is equal to 1. Then I'm gonna say, oh, I have k plus kx squared plus ky squared equals 1. Then I could divide everything. Actually, I don't know why I did that. I could have just divided everything by k, right? So I got this 1 over k or 1 over z, doesn't matter. And then I could subtract. So here we just have some number, right? This is just some number that we don't know. But we're gonna have a circle in this case. So in the xy plane, right? When my z is gone, pretty much, well, I'm gonna have a circle. When my x is gone, so my yz plane, when my x is gone, I'm gonna have z equals 1 over 1 plus y squared. Now, what is that? To me, that looks like a parabola, but we're gonna check ourselves. We could, I could do this, 1 over z. I could say y squared is 1 over z minus 1. And then I can see, yeah, that is a parabola. Kind of looks like one. I don't know. Let's see. So let's say this is a parabola, right? And then same goes. If I take out my y in my xz plane, I also have the same parabola. So they're both parabolas in this case. So I have a circular paraboloid. That's what I have. Um, okay. I haven't found my domain yet. This one's a weird domain, right? Um, my intercepts, if I want to find my x, then that means my y and my z have to be a 0. Then that means uh my y and my z are 0, so I would have something like 1 plus x squared equals 0, which is undefined, right? This is undefined. So I'm gonna say no x-intercepts. So that's one thing. Now, if we do my y, well, then that means my x and my z are both 0, and it's the same idea, right? I make my x 0, I make my z 0. I get the same thing. So that means I have no y-intercepts, which is interesting. Now, if I make my z-intercept, here I make my x and my y 0. So my x is equal to my y is equal to my 0. Here I would just have z is 1. So I actually have 1 point here. That. So that's all the information I know. And then from there, I'm going to check my graph and see which one has the closest. Well, definitely not that. Origin is on the surface. How would I know? I don't really know. Is there like a curious? There like a Desmos thing I can look at. Maybe I can draw it out in 3D. Uh, 3D one. Okay, here I'm checking. Which one looks 1 over, or yeah, let me just do Z. 1 over 1 plus x squared. Yeah, y squared. So there's like a hump in the middle. There's a hump here. And that's Z. And I'm going to safely assume that's a 1. Ooh, so it's kind of. And then my x, I don't know where that is. Yeah, so it's like a hump. Here my x and my y are infinite. There aren't any intercepts. So it doesn't. Uh, so if I zoom in, I'm not touching my x and my y axis. I'm only at my z. And apparently that's also where my maximum is. It's not even a I don't think it's a circular parabola of some sort. I don't think so. To me, it doesn't look like it. Uh, So in the YZ plane, it's a parabola. In the XZ, it's a parabola. YZ and XZ. I mean, yeah, it kind of looks like it, yeah. But that doesn't intersect. Okay, let me find a graph that looks exactly like that. Yeah, I would argue it's that one. Number 3. Number 3. Yeah. How many more do we have? Oh, we have like a couple of graphs here. But yeah, it's just yeah, so it kind of looks like basically this. And then what happens is that there's like a hump, kind of like that. There's a hump here at 1. So I imagine this is my z, my x, and my y. And I think the traces, right? We have a circle in my xy, kind of like this. Then we have a parabola, and it actually goes down, right? It's concave down. So I would say like that. Then we have another one like this. I'm not super sure. And here it doesn't intersect the x and y axis, so it would look something like that. Yeah, I'm just gonna double check, see if I got it. I hope I did, kind of. Uh, okay, yeah, we got that. Cool. Okay. I'm gonna stop sharing this. I'm actually gonna show my screen here. Um, because I think this one's a better way to look at it. Okay, now we're given this next function here. Oh, I can't zoom it in. We have 1 over 1 plus x squared y squared. So here I'm just gonna change this a bit. I have 1 over 1 plus x squared y squared, right? Then here now I have this thing. How do I know? Well, here my domain is 1 plus x squared y squared shouldn't be 0, right? And then if I were to trace this thing, if I take out my x, I make it a 0. Well, that would make my y 0, right? So if I take out my x, let's hold it from this perspective. If I take out my x in the yz plane, so this yz plane here, I would get something of 1, right? If I take out my y, then in my xz plane, I would get the same thing. And this is again a parabola. Those two are parabolas. Wait, no, actually, no, they aren't. Which is weird. They aren't. And then if I take out my z, I make it a 0. Or no, if I just take out my z, I'd get something interesting. Because I'd get a k. Yes, if I substitute this with k, I get like 1 plus x squared y squared equals 1 over k. And I get x squared y squared equals uh 1 over k minus 1. So I'm gonna admit I don't know what that function is. But yeah. Oh, am I doing that? Then if we kind of zoom it out, it's kind of infinite. But again, there is no y or x intercept. Yeah, because it's not intersecting it at any point here in this case. Yeah. So, oh, so which one looks like it? Oh, okay, definitely not that. One of these. It goes here at 1. Here it also goes at 1. Also goes at 1. It doesn't intersect the axes, right? Here it also doesn't intersect the axes. Uh, what else? Uh, what can we say about it? Actually, I can't even see it. So it intersects the z-axis at 0, 0, 1. It has a surface between 0 to 1. This one's a surface between negative 1 to 1 of my z. Really? Oh, it is. Negative 1 to 1. Here it's from 0 to 1. So that's the difference that we can. Yeah, but here, see, it doesn't really go down my z, right? And I think the reason for this is something about domains, right? If we say this shouldn't be 0, can I say, can I say, if this thing, if this thing shouldn't be 0, then this one should always be positive or something like that. I'm double checking what I did. I think that's the case. I know I highlighted it somewhere. I just forgot. Something about domains. Let me see. Oh, now I remember. If I were to switch this up, I make it 1 plus x squared y squared equals 1 over z. Because I could do that. I could modify that. Then z should not be 0. It shouldn't be 0, right? That's why it doesn't intersect the origin in this case. But then what's weird is that it's also not negative. It's probably like some function of, I don't know what this is, but it's 1 plus x squared y squared equals 1 over z, right? I just switched this term uh, to this term. So I get, basically what I'm saying is 1 plus x squared y squared equals 1 over z. So I should get the same thing. Let me take that out. I should get, oh, what is that? Why did that turn different? Oh no, it's just yeah, it's just yeah, yeah. It's the same thing. This is the same thing. But yes, it shouldn't, there we go. It shouldn't intersect 0 in my z. But then what's weird is that it shouldn't also go down. So what happens if this is negative? Oh, because if I square these, then it's positive. So z shouldn't also be a negative value. So yeah, that's right. So I would argue it's this value here, where it doesn't, yeah, it's in between 0 and 1. I would say it's, yeah, number 1. Let me see if I got that. I'm a bit scared though, but we'll see. Should be one though. Okay. Yes, we did get it. Okay. The next is ln x squared y squared, x squared plus y squared. So if I just graph this, I have z plus ln x squared. I add it to my y squared, and I get this thing. Why I do that? There we go. So where are my conditions here? Well, my domain should be uh, x squared plus y squared. It should be greater than 0, right? So we actually have a domain here, which is this bottom thing here, where x squared plus y squared should be greater than 0, right? Okay, let me zoom out a bit. Oh, it looks like a plan. I don't know what that looks like. And then from there, okay, let's go to this form. Let's go to the first octet. And then from there, so that's our domain. How do I identify this curve? If we take out my x, I make it a 0, let's say. I get the natural log of y squared equals z. And then I could say e to the z is equal to y squared. I don't know what that is. Is that a parabola? I think that's a parabola. So in my xz, I have a parabola. No, I have a, no, I know. I have a parabola. Because in my xz here, it looks like I have a logarithm. Yeah, it's a logarithm. If I take out my x squared, I just get z equals ln y squared. It's a logarithm. And same thing, if I take out my x, if I look at my yz, I also get the same logarithm here. That thing that looks like a logarithm, logarithmic function. And then if I take out my z, so on the xy, well, I basically get x squared plus y squared equals 1. I get a unit circle. So this one has a radius of 1. This should have a radius of 1. Yeah, I can't see. Yeah, it's 1. Radius of 1. So it's a unit circle. So this is so we have a logarithm and then a circle. I don't know what that is. Uh I mean I don't know how you call that. Yeah, now we've identified the traces, and then from there we need to find our intercepts. So if we want our x-intercept, and so actually we do have it here, we'd make it we make y and z 0. So we're left with 0 equals ln x squared. We take the natural log, we get 1 equals x squared, and so x is just negative 1 and 1. And then same goes with y, negative 1 and 1. For my z, we actually don't have an intercept. It doesn't, my graph here, or my surface, doesn't touch my z-axis at all, right? It doesn't touch my z-axis at all. Why is that? If I make ln of 0, well, that's a domain error. If I make my x and y 0, that's a domain error. ln of 0 does not work. That's why z here in this case doesn't have a z-intercept. Yeah. And so from there, I could say, which one of the graphs is it? I think is it this? No, that's weird. It doesn't look like that. Okay, some of them is loading. Oh, I think it's this. Yeah, here it doesn't intersect. It goes from negative 1 to 1 for both my y and x axis here. And so I would argue it's this graph here, number 4. So here really, the idea is we're just identifying what graph it is based on its domain, its traces, as well as its intercepts. So I would argue that's 4. Let me see. Okay, cool. Next, let's just go through it. We have cosine. So probably something that square root of, let me do this. Square root of x squared plus y squared. There we go. Great. It looks like that. So again, I can just ask what my domain is. Well, my x squared plus y squared should definitely be greater than or equal to 0. And so from there, that's going to be what? It's going to be this, basically. Yeah. Okay. And then to identify my traces, if I take out my x, I'm left with cosine of square root of y squared. So I'm left with z equals cosine y. I'm left with that. So if I look at my xz, no, my yz. My yz, where's my y? Oh, there. My yz. So I'm looking at it from here. Well, here you can see I just get a cosine curve. I just get a cosine curve, right? And same goes for my x. My xz also gives me the same cosine curve right there, x and z. And lastly, if I take out my z, I make that a 0. What would I get? I make that 0. So I look at my xy plane. I'm gonna look at it this way. Y and x right here. So if I make my z a 0, I can just divide it. Doesn't matter. I could get the arc cosine of 0, right? Which would equal square root of x squared plus y squared. And the arc cosine of 0 is 90. I'll make it in radians. So that's pi half. Pi half is square root of x squared plus y squared. I could square that whole thing. So I get pi squared over 4 is equal to x squared plus y squared. And so here I basically just get a circle, and my radius is pi half. So that's why I get, oh my goodness. So this should be pi half, or 1.5 something, which kind of looks like it. Yeah, I'm not going to doubt my math. I would say, yeah. So if I take out my z, I'd be left with a unit circle, which is the center here at 0, 0. Oh, why do I look like a, why do I look like that? With my center there. That's funny. Oh my goodness. Okay, okay. Okay, okay. I'm not used to this. Okay, chill. Okay, then I'll just leave it like that. Okay. Yeah, so it would have that, and then my radius is pi half, right? So let me just see which one looks. I'd argue it's this one. Because it's one here. And there's the cosine curves, right? For my xy and my xz. And then from here, it's a unit circle. Let me read the graph. Should have something there, right? Okay, it's either that, definitely not that. Oh, I can't see it. Not this. Number 3. It's not that. It's not that. It's not that. Yeah, so I would say it's this one. This is the closest one we can find. So it's number 5. This is number 5. Okay. Let me see. Nope, we got it. Nice, we did get it. We have 2 more. So we have z is equal to the absolute value of xy. Okay, so I get this. I don't know what that is. I think it's this, right? I'm gonna be honest, I can't even tell. We already, I think we looked at this. Yeah, we looked at 4, we looked at 3. We looked at 1. We have 2 here. And yeah, it's only between here I'm just doing a process of elimination. 1, I'm left with 2, 3, 4, 5, 2 and 6. So it's either this or this. I would argue this one is 6. I think it's 6. So let's just go for it. And this kind of looks like it. Yeah, I would say it's 6 in this case. And so this one makes it 2, right? My cosine xy. If I get, oh my goodness, what am I looking at? I'm looking at wavy waves. Yeah, this one makes it 2. Okay, actually, I'm not super sure. Oh, this is from 2. What is this? Yeah, that looks about right. It's not showing the whole thing. Nice, we got it. Okay, now we're gonna proceed to talking about contour maps. So let me just go there real quick. I'm gonna do this in one whole video. Okay, it's all about contour maps. So, contour maps. Let me just go to my stuff here. Here, let's sketch the graph. Level curves and contour maps. Okay, I'll just go through the basics and then we'll see what we can do from there. So, level curves. And contour maps. So here we talked about 2 methods for visualizing functions. Well, we did arrow diagrams, we did graphs. And here you actually have another method for doing it, which is a contour map. So here, we basically look at points of constant elevation, which are joined to form contour curves or level curves. So what in the world did I just say? Let's do a definition. So it starts off with a definition. So the level curves of, let's say, some function f of 2 variables are the curves with, okay, let me just, function f of, here we're assuming it's 2 variables. Are curves. So these are curves, and they have equations f of xy, which is equal to k. And here k is some constant. Here we say k is constant in range of f. So that's what we're saying. So a level curve of xy equals k is the set of all points in the domain of f at which f takes on a given value k. Right? So it takes on a given value k. And in other words, it is a curve in the xy plane. that shows where the graph of f at height k, above or below the xy plane. Okay, so we're gonna say, basically, oops, this thing, f of xy, which outputs k, is a curve in the xy plane. So it's some curve that we can see in the xy plane. And it shows where the graph of f at height k. Okay. That shows graph or visual of f at height k. We're going to see some examples maybe on how this works. So at height k, meaning since our k-axis varies, right? So we're assuming this is the z-axis. This is z equals k. So maybe at a certain height, it has a different curve than, let's say, when my z is 0 or in the xy plane. So we're saying height k, which just means either above or below, or maybe on, doesn't matter. Above or below my xy plane. So we'll have like different graphs. And we're saying that a collection of these, so we call these level curves, because at a certain level, they have a curve. Very original. A collection of level curves is what we call a contour map. No, I don't know why they named it that way. And contour maps are the most descriptive when the level curves f of xy equals k are drawn for equally spaced values of k. And we assume that this is the case unless indicated otherwise. So we actually have some figures here. So let me take a screenshot of these figures. It's not really like computational math. It's more or less visualizing. It's more in the visuals. Okay, so let me just take. So here we have some figures. We'll call them 11 and 12 in this case. And in these figures, we can see from figure 11 the relation between level curves and horizontal traces, right? The level curves f of xy equals k are just the traces of the graph of f in the horizontal plane z equals k, projected down to the xy plane. So if you draw a contour map of a function and visualize the level curves being lifted up to the surface at an indicated height, then you can mentally piece together a picture of the graph. And the surface is steeper where the level curves are closer together and somewhat flatter when they are farther apart. So here we can see that these are the level curves. This is the contour map. This thing's the contour map. These are the traces of our 3D shape. Okay, I don't want to vandalize that. Yeah, so these are the horizontal traces. I believe this is the vertical trace, right? Not sure what you call this figure. It looks like a hat. And then at a certain K, we have that corresponding horizontal trace. And we call these red things level curves. Yeah, they highlighted it. And a collection of these level curves, right? So that whole thing is a contour map. And so this helps us identify, or this gives us some perspective on what the shape is going to be in 3D. So yeah, one common example of level curves occurs in topographic maps of mountainous regions, such as the map in Figure 12. Okay, what else? Okay, there's a lot more about contour maps. I'm not gonna dive into it. Okay, let's look at an example here. Then I might immediately go to. Can I go immediately to it? Oh, I'm just gonna use it to make a rough sketch of my. Oh, that's funny. So I wanna sketch the level curves. Um, Yeah, I'm gonna skip some examples here just because I might. Yeah. There's also three variables, which is funny. Okay, let's do uh yeah, let's do one example and then we can just hop into the exercises. Okay. Uh yep, let's just do it. So here we want to sketch a contour map. I want, not sure. Let's just go for it. So we have a contour map for a function f is shown in figure. Okay, you have a figure here. That's funny. Uh, actually, no, let's do a different one. That's fine, it's fine. Let's just do this. Okay, so we have a function f. So we have a contour map for a function f. And I'm assuming this is a function of two variables. And here we use it uh, in order to estimate values of f of 1, 3, and f of 4, 5. So again, this is a function of two variables. Now I'm going to show the contour map just so we can see what it looks like. Okay, let me quickly show what this is. Okay, so we have this contour map, and we're being asked to find or to estimate the values of these two functions. So here we see that f of 1, 3 lies partway between the level curves with z values 70 and 80, right? So if we look at 2, 3, 2 for our x, right? Or no, 1 for our x. My bad. 1 for my x, 3 for, so it's somewhere here, right? And here we can see that uh, it lies partway between the level curves with z values 70 and 80, right? And so from here, we can actually just estimate. So we can say my f of 1/3 is around like somewhere in between 70 and 80. So the textbook says 73. But yeah, it's somewhere there. Then the other one was f of 4 and 5. So I would say here and here. So here. And where is this in between? It's between 50 and 60, right? So it's between this curve, this curve. That's the horizontal trace when z is 50, and then this other horizontal trace when z is 60. So it's somewhere between those two. So my f of 4, 5 is somewhere between 50 and 60. So we'll just do 56. Yeah, that's the idea. As one other example here, maybe. Um, actually, never mind. You can just do that someplace else. These are just sketching the level curves, and then that's it. Okay, let's go directly to our examples in my homework. Okay, so here we're being asked, did I just graph these things? Or no, oh, yeah, I did. Okay, my number 8. So here we're given a contour map, and we use it to make a rough sketch of the graph. Here we make sketch of function f. Okay. Select update graph to see a response. Okay, let's use this contour map. Well, technically, we're just writing equations, right? So here we need to identify. Actually, this is a bit funny because we're given one of them. So yeah, it's a bit funny. Yeah, I just realized the examples in my textbook were more of given my function of two variables, what's the contour map or sketch the level curves, right? But then here in my exercises, given the contour map, what are the level curves? So it's a different way of looking at it. Yeah. I might still go through this just for fun because definitely these look interesting. Okay, let me just go through these. Yeah, so I write, what am I doing here? Okay, so I have this contour map, and the first thing I want to do is to write the equation of the curve. For the cross section, write an equation. For cross section, z equals 1. And here I use x and y, right? So it's one of these problems again. So here we see, oh, z equals 1 right here. Oh, crap. Why did I use that? I should have used this. Z equals 1, that thing. And so what's that equation? Well, to me, it looks like a circle. And it's the center of the origin. So I would say it's a circle. My center is the origin. What's my radius? Okay, if my judgment is right, I think this is a 4, a radius of 4. So I would say it's a radius of 4. But again, I might be wrong. Because when I count this, I see, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's by 1. So I just counted. Anyway, that's my idea. So at z equals 1, my level curve is x squared plus y squared equals 16. So yeah, that purple thing I just traced, this trace, is basically x squared plus y squared equals 16. Let me just type that and see what happens. See if I get it. If I don't, that's totally fine, because it's my first time seeing such a problem. Uh, oh, cool, got it. Okay. It also has an equation for z equals 3. So at z equals 3, well, I have this one equals, what was this? 4.8 squared? 4.8 is such a random number too. Yeah, so that's the radius. Yeah, I can't really estimate that. Yeah. Okay. We have another right an equation for this cross section. So here it's more of graph looking. Okay, here I give another one. This time when z equals 1. So if I look at my graph, wait, no, not z equals 1. I already did that. 5 when z is 5. So when I look at the level when z is 5, I see this. I see that. Now, what is this? Again, it's God, there's too many circles. Again, this is a unit circle. It has a radius of, I believe that's a 6. That definitely looks like a radius of 6. So I would say x squared plus y squared equals with a radius of 6. So I square that, I get 36. Done. I think it's that. Contour maps are really cool because I was first introduced to them in one of my intro to scientific computing videos where I talked about an intuition for gradient descent. I saw some contour maps there. Okay, next when z is 7. Okay, let me save the hassle and just copy and paste. So I'm doing this again and again. So now I'm saying when z is 7, what is this? Uh, when z is 7, 5, 6, 7, 8. Now my radius is 8. I have 8 squared. I have 64. There's no pattern or anything. It's just, oops, typed it wrong. I got, yeah, 64. 6, 7, 8. Yeah, okay. 6, 7, 8. Yeah, okay. And lastly, let me guess, 9. Yeah. So when it's 9, it's just what? 10, 11, 12. So I have a radius of 12. So lastly, when it's 9, and the eraser is not working again. Nice. I can't write anymore. Good. Okay, let me, how do I get this to write again? Oh, there we go. Shoot, we got it. Okay, then this is 9. So I get 12 as my radius. And so 12 squared is just 144 if I did my math correctly. Yeah, I would say it's this. Because they're all unit circles. Oh no, they're all circles, not unit. But yeah, let me hit submit, see what happens. Okay, got it. Next. Now you have again a contour map. So actually we do the same thing. So for number 9, so we use again the contour map to sketch my function, which we'll call f. Oh my goodness. Okay, so I have this. Okay, so these are a bunch of parabolas, and I cannot tell what my z value is, right? It's just a bunch of parabolas. Uh, so I just have to assume it's something parabolic. Oh my goodness. I cannot find. They all look the same. That's funny. Okay. Jeez. Why do they all look the same? Uh, um, okay. Maybe. Oh, actually, I could find some domain and stuff here again. No, I actually can't. I don't think I can. It's weird. Okay. Uh, Trial and error maybe. Okay, let me actually see what the difference is. So it intersects the x-axis. Oh my God, they intersect the x-axis. Oh shoot. They intersect the x-axis at almost the same point. Okay. Uh, oh no, they do. Okay, except this one. So this one, okay, it intersects the x-axis at -4 and 4, which should. It does. It does. Okay. The surface intersects the y-axis at -4 or 4, -4 and 4. This is a deal breaker. Which one is it? Does it intersect at 4? No. See here, it only intersects. So it intersects the x-axis at 4 and 4. Done. I'm going to be biased and say that that happens. And it intersects here at -4. But now what's funny is that this one is a negative and this one's positive. Uh, oh, look at that scaling. Is this? Oh no, this is negative. No. Yep, I'm confused. Uh, 1, 2, 3, 4, 5. Why is the negative here? Then I have a 10 and a 5 here. Uh, oh, the levels. I'm assuming these are the levels, right? And then this 8 is also a level. Yeah, this is a level. Okay, cool. Here we also see a negative 1, 2, 3, 4. So here it intersects as well. 1, 2, 3, 4. Okay, so here we can actually see that it has x-intercepts, which are -4 and 4. So so here we can see that we can deduce that. For my y, I only have one, right? 1, 2, 3. Yeah, this one doesn't touch. So I'm gonna say my y intercept is only one, which is -4. So that's the deal breaker there. Now I can get rid of my two things here. So I have to choose between, well, what else is the difference? Oh my God. Oh, now we look at domain. So the surface is between what? -8 to 10 or -10 to 8? Now we see. -8 to 10 or -10 to 8. 10. How do I indicate that? Can't see. Negative, what is this? Oh, this is -8 and 10. So the surface, what it's saying here is between -8, y equals -8, and y equals 10. Can I see that? Is it in between -8 and 10? Or -10 and 8? Here, definitely. It doesn't touch here at any point. So I would assume it's the other one. -10 to 8. 8, -10 doesn't. Wait, let me just draw it. Negative 10 to 8. Or the other one was negative 8 to 10. Here? Oh, God. I'm gonna have to go for the other one because this one I think suits more, right? So negative 8 to 10, I would say. Yeah, I think it's negative 8 to 10. Negative 10 and 8. Yeah, I mean, yeah, yeah. It's 8 to negative, it's, what is it again? It's negative 8 to 10. Yeah, because that's where it has a trace right there. Here, I would say it's that based on the contour map, right? Doesn't even touch negative 10 here. So I'm just gonna have to go for this one and just hope it works. So, I mean, that's how we can use contour maps. You can, again, just track the traces. Oh, we got it. Look. Okay, nice. Okay. Number 10, same idea. We're given a contour map, then we sketch my function. Let me just put this in. Okay. So here I just have to differentiate stuff. I have to see how many times do I have to do this? I have to do this for all of them. Read, draw. Okay, one is. Oh, okay, okay. Let me. You know what? I'm gonna stop sharing. I'm gonna switch to that because it's easier to go here. So let me just go here. Okay, let me just go through it. Uh, Great. We're here. So here you have a contour map of a function. We use it to make a rough sketch of the graph. So these are the levels, right? At z is 1, 2, 3, 4, 5. This is my y-axis and my x-axis. And here I have like lines, which is weird. Uh, okay, which one is it? Oh God, they all look the same. Okay, let me look at it from a first octet perspective. So I'm just gonna do that. Okay, this one's in reverse. That's funny. Okay, this one's a bit like flat. And then this one as well. Okay, they all look the same, which is funny. Let's see. So at z equals 1, should have a curvy. These are curvy, so I can immediately eliminate these two. So I would just look for these two. Which one looks... Look at it from here, actually. It's kind of like slanting. You can see that. Here it's straight, right? I'm just judging it based on the curve. This one's slanting, this one's straight. What's this? I think it's slanting. I'm gonna say it's this one. Let me watch it. Is there like a... Yeah, I want to watch it thing. Or unless he's able to trace it on his own. Oh, he can trace it on his own. Whoa, that's crazy. Yeah, I can't do that. That's crazy. He can actually trace it on his own. That's funny. I just looked at the watch it thing. I would say it's this one though. Okay, let me hit submit, see what happens. To me, it's more like a drawing thing instead of math. Uh, Oh, I didn't get it. That's funny. Okay. So which one is it? I want last try. I don't know which one is it. This one. It's not straight. That's the thing. So it's probably this one, right? I would say it's this one. More steep. This is off by, bro, it's off by like 0.3. It's probably this. It's off by 3. And it's not, is it parallel? I don't think it's parallel. Okay, I'm gonna say it's this one. If I don't get it, that's all right. I just need, if I don't get it, that's okay. Okay, good, we got it. Next. Contour. Use it. What is this now? Oh my God. So, okay. At 0, it's here. At 1, okay, this one's more of a drawing thing. Okay, wait. At negative, it's wider. Oh, so it's like this, right? Negative all the way to 3. So it's not either of these. It goes all the way to 3. Should go all the way to 3. So I'm thinking of this. It goes all the way to 3. It's more like a fun drawing thing. That's funny. Hey, got it. That one's really cool though to draw. To try and draw like at every level, draw the curve, and then like make a 3D out of it. That's funny. Okay, we draw a contour map based on a function here. So here's just the reverse. So I think this one's personally easier. X squared minus y squared is an ellipse. It's an ellipse. Um, Let me just do my calculator here. It doesn't matter. I can judge it from the graph. There we go. So if I look at my my XY plane like this, oh my goodness. So it looks something like that. Oh, it's a hyperbola. It's probably that. Yeah, it's this. Right? Done. And again, draw a contour map. So it's really just a visual. Y e to the x. What's this? It's an exponential, but I don't know where it's heading. Hmm. If this was some k value, what would it look like? Trying to think. I can't imagine how this would look like in terms of like 3 variables in one go. Oh my goodness, what am I looking at? Saw it from the where's my oh there you oh like this. So it's like an exponential kind of thing. Like this. Wow. It actually looks like this. Yeah, I mean here I just identify my traces. If I make z nothing, I would just get a regular e to the x. If I make it like a k, uh then my xy plane would be yeah, something like this. If I just divide my y, yeah, I would get 2 things. I would say it's this. We can double check though. Yeah, so we make it a k. Oh, and then we do y equals k e to the negative x. And we plot points. And then my k could be 1, 2, and 3. Yeah, we could do that. That one's fun. Yeah, but we'll end up with this thing though. Yeah. Yeah, and I already did this part. This one's just graphical transformations. Yeah, finally, we got all of it done. Oh, okay, that's all for today's video. I hope you guys enjoyed art. Okay, I'm kidding. Math with a bit of art, but yeah, I'll see you guys in the next one.